Some complexes containing transition metal ions are coloured. Explain why some complexes containing transition metal ions are coloured, list the factors that affect the colour, and describe how colorimetry can be used to determine the concentration of a coloured complex. So first of all, why some complexes containing transition metal ions are coloured. So what happens when a transition metal ion forms a complex? The ligands cause the d orbitals to split into different energies. So normally we would say that the 5 d orbitals are degenerate, all of the same energy. But when the ligands interact, they split and they form different energies, and it may be this way up with 3 at lower energy and 2 at higher. Depends on the shape of the complex. And then what happens is the complex absorbs certain frequencies of visible light. This needs to be visible light. It's light from the visible part of the spectrum. D electrons move to an excited state, or they move to a higher energy level. They move up from that bottom state to the higher state. The remaining frequencies of visible light are transmitted. So remember, some are absorbed, the rest are transmitted, and that's the colour you see. So for example, if you're seeing blue, it's because the orange and red parts of the visible spectrum are being absorbed to cause d electrons to move. You're seeing the remaining frequencies being transmitted. So that's bullet point number 1. List the factors that affect colour. So what could affect the colour? Well, the transition metal that is in the complex. So we know that copper 2 complexes are often blue, but iron 2 are green. So that could do it. The ligands that are attached. So for example, when copper has got water ligands, it's blue, but when it's got copper 2's got chloride ions as its ligand, it's yellow. So the ligands. The oxidation state. For example, iron 2 is green, but iron 3 is brown. The coordination number. So for example, hexaaqua 6 coordinate, copper 2 is blue, 4 coordinate CuCl4 2- is yellow. And then the next bit says, describe how colorimetry can be used to determine the concentration of a complex. So you would make solutions of the complex with known concentrations and measure their absorbance. Then you would plot a graph of absorbance versus concentration. So what did it absorb at these different concentrations? In an exam, please ask for extra paper at this time. Don't write outside of the box. I've only got one little point left to write down, so I'm just going to squeeze it in here. So measure the absorbance of the coloured complex and find its concentration from the graph. This graph would be a straight line, proportional relationship. So you could measure the absorbance of your unknown and then read off the concentration from the graph. Figure 5 shows the visible spectrum of the hexaquicopper 2 ion. Use the wavelength at the peak. So wavelength is on the x-axis. The peak is here. So we can see that that wavelength at the peak is 800 nanometers. So the wavelength is 800 nanometers. To calculate the energy change, delta E, when the electron absorbs radiation with this wavelength. So remembering that delta E equals Planck's constant times frequency, but that is Planck's constant times the speed of light divided by wavelength. Now, noticing that speed of light is in meters per second and this is in nanometers. So we're going to do Planck's constant, 6.63 times 10 to the minus 34 joule seconds. And we're going to times it by the speed of light, 3 times 10 to the 8 meters per second. So now we've got joule meters on the top line. We need to divide by 800, but we need to turn our nanometers into meters. There are 1,000 million nanometers in a meter, times 10 to the 9. So we want to type that on your calculator. So 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 800 times 10 to the minus 9. It's coming out as 2.49 times 10 to the minus 19 joules.